Hello everyone, welcome to the lecture on 3D computer vision, and today we are going to talk about homography and robust estimation. Hopefully, by the end of today's lecture, you'll be able to show the existence of homography in two particular cases, and you will be able to explain the difference between algebraic, geometric, and the Sampson error, and then apply them on homography estimation. Finally, we'll look at the ransack algorithm for robust estimation. Of course, I didn't invent any of today's material. I took most of the slides and the content of today's lecture from the textbook written by Richard Hartley and Andrew Zimmerman, Multiple View Geometry in Computer Vision, in particular, chapter 3 and 4. And I also took some of the materials from the textbook written by Ma Yi, an Invitation to 3D Vision, in particular, chapter 5.3. I strongly encourage every one of you to take a look at these two textbooks after today's lecture. So I've seen in lecture 1 that for central projection, there's a series of transformations that maps a point from one plane to another plane. So essentially what it means is that we have looked at the series of operation or the transformations that maps a point from the P2 space to another point on the P2 space. And we have denoted that this transformation as the as H over here, and it could be a projective transformation, a finite transformation, similar transformation, or a rigid transformation in the Euclidean space. And this is represented by a linear mapping of homogeneous coordinates, and which is given by this particular equation over here. H here is the linear mapping transformation, which maps a point for x, which is in the P2 space, to another point x prime, which is also in the P2 space here. And today we'll look at this particular transformation in the most general form, the projective transformation, which we will also call it as homography in today's lecture. And we'll look at in particular how to estimate this homography using 4-point ransack algorithm. But before we look at how to estimate the homography using 4-point correspondences from a pair of images, let's first look at the existence of projective homography. There are two cases in particular that projective homography exists due to the fact that it must be a transformation from a P2 space, a point in the P2 space to another point into the P2 space. And in the first case here, it must be in a planar scene. What this means is that suppose that I have a set of points, 3D points that lies in the 3D world. So this is my 3D world, and I have a set of points denoted by these circles over here. Suppose that one of these point, I'm going to call it capital X over here, and the existence of this projective homography is true only when all the points that we see in the 3D world lies on a plane which we call pi over here. And what it means is that when all these points lies on the plane pi over here, the projection into two different views of camera 1 and camera 2. So it will form image 1 and image 2 over here, where x1 and x2 here are correspondence of the or reprojection of the 3D point x into image 1 and image 2 here. There will exist a homography which we denote as H that directly links these two corresponding points over here. So what this means is that when the 3D points over here lies on a plane, then all its reprojections onto the image over here, there will be a one-to-one correspondence that directly is related by h, which we can write as x2 here equals to h multiplied by x1. And this is the first case where this homography or the projective homography exists in relating the two sets of correspondence between two images. They must all lie in the on a plane in the real 3D world. And now let's derive this particular relationship here. Starting from that, suppose that x1 and x2, capital X1 and x2, are the 3D point x. So I have this 3D point which I denote as capital X over here. And what x1 and x2 means here is that I'm representing x in the first camera frame. Suppose that I have a camera frame over here that I attach to this camera and the image, and the x1 here would be the coordinates that is with respect to the camera coordinate frame 1, and x2 here would be the same 3D point x that is represented in the camera coordinate frame 2 here. And we know from the rigid transformation that x2 is going to be related to x1 via a rotation and translation. So this would be the rotation from frame 1 to frame 2, and the translation would also be from frame 1 to frame 2 over here. Now we further denote n as a 3 by 1 vector that represents the normal vector of the plane pi here. And this is a unit normal vector. This means that the norm of n should be equals to 1 here. And this represents the plane pi with respect to the camera frame C1 here. And d is the perpendicular distance from the plane to C1. This means that from this plane over here, from the camera frame over here, we will have a perpendicular distance that this particular plane pi here make with the uh, camera frame C1, and we will denote this distance here as d, and hence the equation of the plane can be rewritten into this form here, into the Cartesian form, which we have seen in our lecture 2 when we talk about the 3D projective coordinate and the rigid transformation of a plane. And here, n transpose x1 here can be rewritten into this format here, which is the normal vector dot product with the x1. X1 is the point in homogeneous point in the image frame here, so which can be converted into an inhomogeneous coordinate x, y, and z here, and hence I will get n1x plus n2y plus n3z equals to d here. And now I can reformulate this, move d to the left hand side of the equation, which will give me this particular equation here that is equals to 1. And what's interesting here is that I have two equations here, equation 1 and equation 2 here. Since equation 2 is equals to 1, this means that I can multiply this term here anywhere here, and it will still be the same relation. Equation 1 will still hold because this equation 2 here equals to 1. So I'm going to multiply this guy here with t in equation 1. So I will have n transpose x1 divided by d over here. And now factorizing out x1 in this equation after multiplying equation 2 into the equation, I would get this particular relation here, combining the two equations and factorizing out x1, I'll get this relation here. And since we also know that lambda x1 equals to capital X1 here, so what it means is that we know that these 2 points here, x1 and x, the 3D point, capital X over here, it lies on a line. Both of them lies on a line. So what this means is that uh, this uh, the a scale of this a scalar product of this x1, the vector of x1 here, if I were to scale it with lambda, I'll be able to reach the 3D point here and represent the 3D point here. Hence the equality in these two equations. So lambda here is actually a scalar uh, scale. It's a scale that I scale up x1 such that I can scale up this vector of x1 into x over here. So similarly for x2, I would also be able to scale this x2 over here, this vector over here, with respect to the frame at C2, such that it becomes the same as the 3D point here in the frame of C2. Hence, that is another scale of lambda 2 here. And substituting these two relations over here with the scale into the this equation that we have obtained from combining equation 1 and equation 2, I would end up with this particular equation here. So I'm replacing x capital X1 over here with lambda 1 small x1. This is my image point, and I'm replacing this capital X2 here with the lambda 2 and small x2 here. And now I can combine these two lambdas together. I can simply rewrite lambda equals to lambda 2 divided by lambda 1 here. And finally, I'll be able to get this equation, which it's up to a certain scale. Ignoring the scale, I would obtain the equation of x2 equals to h multiplied by x1 over here, which is the transformation, the projective transformation equation that we have seen earlier that maps a point in the P2 space to another point in the P2 space here. And we can see that in this relation here, H has a certain expression here related by R, which is the rotation between C1 and C2, the two camera frames, as well as the translation between the two camera frames, and the normal vector of the 3D plane that we have defined earlier, as well as the perpendicular distance between the 3D plane and the camera coordinate frame C1 here. And the second case where homography exists that relates the 2 points or a set of points between two images here, x1 and x2, when this H exists, is that there is a plane at infinity. This means that the actual 3D point that causes these two x1 and x2 in two camera frame here lies at infinity, pi at infinity here. And what this means in reality is that this point that is projected onto the image lies at a very far away scene. Example, from taking from the satellite, you have a satellite image of the Earth where all the objects on the Earth are actually at a very far away scene, and that would appear to be the ground of Earth would appear to be at pi infinity, the plane at infinity. And we can see that in this case here, taking the homography that we have derived to be this relation, in this case here is a finite scene where the scene has to be a plane, lying on a plane. That means that all the 3D points, they will have to lie on a plane for this homography to exist, such that it relates to points, a pair of correspondences between the two images. And in this case here, we saw that the plane at infinity simply means that the distance has to be close to infinity. This means that the distance between the camera frame 1, C1 here, and the plane, it has to be close to infinity. This means that D has to approach infinity here, and hence this plane here would be close to the infinite plane here. And substituting this limit into this equation, we can see that this guy here becomes infinity. So this term here will tend to 0, and we will be left with rotation. What this means here is that a very far away scene would the point that is projected onto the two image would be related by the homography, as well as if my camera undergoes a pure rotation. That means that I'm purely rotating this camera, the frame here, along a certain axis here. Then the points that is seen by the two frames would also be related by the homography. And this is similar to, it has a similar effect to the point lying at the plane at infinity, which we can see that from this limit theorem over here, that at the end we will see that both have the same effect as pure rotation here. The next question to ask is that given two images where we have a set of correspondence that where we know that the homography exists, we want to compute the homography from these point correspondences. For example, in this case here, we see that there are 4 point correspondences here. That we know that x1 is corresponding to x1 over here. They belong to the same point, but at a different viewpoint. So there is a certain rotation and translation that relates the two camera centers for these two views over here. And now we identify the correspondences, the point correspondences that are the same point in 3D that is projected onto the 2D view over here. The question is that if we are able to identify these correspondences, how can we compute the homography that relates x prime and x in the two views? And the next question is that how many or a minimum of how many point correspondences are needed in order to solve for the homography that relates these two views here. So as I've mentioned, the question is how many point correspondences are needed to compute H. So the answer is very straightforward. It depends on the number of degrees of freedom in the homography matrix H and the number of constraints each point correspondences give. And we know in lecture 1 that a homography consists of 9 entries with one less for the scale. This means that a homography has 8 degrees of freedom altogether. And we will see that each point correspondences of xi and xi prime in the two image over here. Each point corresponds xi as well as xi prime. These are correspondence. They give us two constraints, and as a result, altogether we will need 4-point correspondences because each point gives us two constraints, and we have altogether 8 unknowns in our homography matrix to solve. So 4 correspondences would give 8 constraints, and 8 constraints, 8 unknowns over here. We will be able to solve for the full homography matrix up to scale. And it will be seen that if exactly 4-point correspondences are given, then an exact solution for the metric of H is possible. And this is what we known as the minimal solution, which is important for ransack loops. We'll see that the more number of points that we use, increasing number of points that we use, or correspondences that is needed in order to compute a certain entity, such as the homography matrix, then the number of ransack loops that is needed for robust estimation will increase exponentially, and this is not good. And since the points are measured inexactly, what this means is that the points here, an image is actually a sensor, an imaging device, which is subjected to noise. This means that every pixel, the projection of the real 3D point or 3D structure onto the image, onto the photo sensor, it's usually corrupted by noise. So it's not that precise. There might be some noise error here and there. And so these point correspondences that we obtain, and it might not also be the exact correspondence. It might be corrupted with some noise as well. So in terms of the location. And under this kind of situation, we'll see that we'll use the least square estimates or the least square solution to eliminate or to minimize the noise in our measurements. Now let us begin by looking at a simple linear algorithm for determining the projective homography, denoted as H here, given a set of 4-point correspondences xi and xi prime, where I equals to 1, 2, 3, and 4. And we'll start by looking at the familiar equation of the transformation, the projective transformation, which relates the point correspondences in two views here. So this is a projection from xi that transform xi to another view of xi prime, and this transformation here is related by h, where the mapping is from the P2 space to another P2 space here. And we'll start off by looking at this equation here, where the unknowns are found in H over here. So there are altogether 9 entries over here, where only 8 of them matters because the scale cannot be found here. And here, xi and xi prime are the 4-point correspondences that we can obtain from the image correspondences using something like a sift algorithm or the surf algorithm, which I will not cover in detail in this particular module. And now the objective here is that starting off from this equation, hxi equals to xi prime, where we have a set of unknowns in H and a set of known correspondences in X. So where one I here equals to 1 to 4, 1, 2, 3, and 4. And we'll have 4 sets of these equations over here. So we'll our objective here is to reformulate this into a homogeneous linear equation, ax equals to 0, where x here consists of all the unknown elements in H, and this would be a 9 by 1 vector, and a here would be all the coefficients from the known correspondences that we can observe from the image. And we can do this by simply taking the cross product of hxi equals to xi prime here with xi prime itself. So we will do this by taking xi prime cross with hxi equals to xi prime cross with xi here. And we know that any vector, when it's cross product with itself, this guy here is going to be equals to 0. Hence, we'll get this relation over here, where we can rewrite h here into the respective rows, H1 and then H2 and H3 here. So we can take the product of each row with X and to form this H multiplied by Xi over here. And I prime over here would be our 3 by 1 homogeneous coordinates from the image, the second image where xi is observed, xi prime here is observed. And the cross product here, substituting these two terms over here into the cross product term over here, we can see that it explicitly gives this equation over here. So factorizing out the unknowns of H, the terms of H from the cross product metric, we can see that we can rewrite it into this particular form here, the linear form over here, where we have a known coefficient metric over here multiplied by a vector. This is a 9 by 1 vector that consists of all the unknowns in my homography matrix H here. And what's interesting here is that this particular matrix, the coefficient matrix, which is 3 by 9, but only two of them are linearly independent. Two rows are linearly independent. This is because if we take x prime I multiplied by the first row and add it to the product of yi multiplied by the second row, we will be able to obtain the third row up to a certain scale. And this means that only two of the rows are linearly independent. Hence, this will give us two constraints over here. Each point correspondence is going to give us two constraints. This is going to produce a 2 by 9 matrix here, where the unknowns here are 9 by 1, or the H in my 3 by 3 homography matrix here, which I can rewrite into this form here, AI H equals to 0. And since we altogether have 9 unknowns, or where 8 of them, 8 degrees of freedom matters because the scale cannot be found, and each point correspondence give me two constraints. This means that altogether I'll need 4 point correspondences. So 4 multiplied by 2 constraints is going to have 8 constraints, where to solve for the 8 unknowns or the 8 degrees of freedom in my homography vector over here. This means that with the 4-point correspondences, I will be able to solve for the 9 by 1 unknown vectors in my H matrix over here. And as I mentioned earlier, that each AI here is going to be a 2 by 9 matrix, because each point correspondences give us two constraints, and H here is a 9 vector that is more explicitly here, it's made up of each entry in my homography matrix, where I write H1, H2, H3, H4, H5, H6, and H7, H8, and H9 that forms my small h, the vector 9 by 1 vector over here. So this would be H1 all the way to H9 over here. And note that in our expression W, the correspondence xi equals to xi, yi, and wi over here. Transpose this a homogeneous coordinate of the point xi in my image. The w over here is normally chosen as 1. This means that I'm going to normalize, divide by w throughout here, such that I will be able to get xi divided by w, yi divided by wi, xi, and then I get a 1 over here transpose. And since H has 8 degrees of freedom, as I mentioned earlier, and each point correspondences give 2 constraints, this means that a minimum of 4 point correspondences is needed to solve for the 9 by 1 factor of H, where each point correspondences is denoted as xi and xi prime over here. And since each point correspondences is going to give me ai H equals to 0, where this is a 2 by 9 matrix, and this guy over here is a 9 by 1 vector. 4-point correspondences means that I can stack them up together. The A1, A2, A3, and A4 here, I can stack them together, and they will still multiply by H equals to, and it will be equals to 0 here. So this means that altogether I will get a 2i by 9 matrix over here, which I collectively call A over here. So note that it need not necessarily be just 4-point correspondences. This is a minimal requirement in order for us to solve for the 9 by 1 unknown in the null space equation here. We'll see that stacking more than 4-point correspondences together, we'll be able to solve for the least square solution that is robust to noise. And in the real life images, as I mentioned earlier, that the measurements of point correspondences are usually corrupted with noise. This means that given an image, the correspondence in the other image over here, because these are mapped onto or captured by real photo sensors, which is subjected to noise, and the algorithm that we use to extract the point correspondences are also subjected to a certain model noise. This means that the 2-point correspondences here, the pair of correspondences here, they might be corrupted with some noise in terms of the homogeneous coordinates here. And what this means is that if we were to put all these correspondences, xi and xi prime here, into our equation of ah equals to 0, this means that if we have a minimum of 4 points, we are going to solve for a minimum for using 4-point correspondences to solve for all together the 9 by 1 unknown here. It's going to give us a less accurate estimation. This is because the point correspondences are corrupted with noise. And an exact solution for this AH equals to 0 does not exist. This means that even if I get the best H over here, after I solve for H over here using the 4-point correspondences, and I plug this H back into this equation with the 4-point correspondences that forms A over here, it's not going to be equals to 0, because all my correspondences, the 4-point correspondences, are actually corrupted with some sort of noise. And instead, we seek to minimize AH over H subjected to the constraint of the norm of H equals to 0. This means that since we know that the point correspondences are corrupted with noise, it's impossible to reach this constraint over here, or to reach this cost over here, such that we can never find a H such that it actually fulfills the equation of A multiplied by the H that we found equals to exactly 0. Instead, we will seek to minimize the norm of A multiplied by H. So we want to get this guy here as close to 0 as possible. But we know that this is impossible because it's corrupted with noise. Hence, we minimize this. This means that I'm going to do an argmin of H over the norm of H, subjected to the constraint that the norm of H should be equals to 1. This is because if we didn't have this particular constraint over here, then the minimum of H here that minimizes this norm could be actually equals to the 0 vector. And this is not a solution that we want, because we don't want a trivial solution for our homography matrix. And subjected to 1, it's also because that we do not know the scale of our homography matrix. Hence, we will just normalize the scale to 1 here. And this is the least square solution of H, which can be obtained by the right null space of A, since this AH equals to 0 is the famous homogeneous linear equation that we know of in linear algebra. What this means is that we can simply take the right null space of A, and that will give us the null space vector of H over here that fulfills this constraint or this optimization cost over here. So the least square solution of AH equals to 0 can be given by the computing the right null space of the matrix A over here. A here is a 2i by 9 matrix where H here consists of all our 9 by 1 unknowns in this null space equation. And by computing the right null space of A, we can compute the solution to this least square estimate. This means that we are computing the solution to the minimization mean of over H of AH such that subjected to the constraint that the norm of H needs to be 1 over here. And we can make use of the singular value decomposition to compute the solution of H that minimizes this constraint here. And this is given by the right singular vector that corresponds to the smallest singular value or the eigenvalue in the singular value decomposition of the 2i by 9 matrix of A. We can see that taking the SVD of A, the matrix of A, 2i by 9 of A, we will get the left singular vector. This is a square matrix, or the left octagonal matrix, which we denote as U over here. This is of size 2i by 2i. And the singular values matrix over here, which is of size 2i by 9, since A here is a non-square matrix in general, this would be a 2i by 9, where we will see that the first 9 rows over here, the diagonal of the first 9 rows are non-zero entry, which corresponds to sigma 1 to sigma 9. That corresponds to the 9 singular values of this matrix A here. And the subsequent rows over here that make out the subsequent 2i minus 9 rows over here, they will be all padded with 0, as well as the non-diagonal of the first 9 rows. They are all zeros over here. And we also have a right singular vector denoted by V over here, which is 9 by 9. And we can see that the multiplication of these three matrices, the left singular vectors, or the left octagonal matrix and the right octagonal matrix, and the singular value matrix over here, will all together, it will result in 2i by 9 of our A matrix here. And after computing this, in general, for a given n by M matrix where M here is more than N, this means that A here it's a tall and thin matrix. We will get the after taking the singular value decomposition of A here, we will get M by M left singular vectors, and the singular value matrix would be M by N over here, where the first n rows over here, the diagonal should be a non-zero value, or that corresponds to the eigenvalues or the singular values of the matrix A, and the rest of all the remaining rows here, the remaining n minus n rows here, it's going to be padded with 0. And we will also have our right singular vector, which is in general n by n in size. We can denote this as U sigma and V transpose here, and this will give us the matrix of A. And in the case where A is not corrupted with noise, since A here we mentioned that it's formed from the observation, from the correspondences between two images, xi and xi prime here. And in the case where all these correspondences are perfect correspondences, they are not corrupted with noise, then an exact solution of AH equals to 0 exists. And what this means is that the rank of A here, the rank of A here is going to be exactly R over here, where R is the number of point correspondences or the number of constraints in H here. So since in our homography estimation case here, it's going to be uh, 2i by 9, where uh, we are only interested in 8 unknowns, or in this particular 9 by 1 vector here, there are only 8 degrees of freedom. So what this means is that the rank of A better be equals to 8 in order for us to find the this particular solution here. But in general, the this does not exist because the point correspondences are corrupted with noise, and in general the rank of A is not going to be equals to 8 over here. And we'll see that in this case, if A is corrupted by the noisy measurements, so what this means is that the next n minus r singular values, they are not going to be equals to 0. So in the case where, in the previous slide here, in the case where the rank equals to 8 over here, or exactly equals to R over here, then the singular values of all the uh, n minus r singular values over here, the least singular values over here, they are all going to be equals to 0. But in the case where they are not, the rank of A is not equals to R, then these least singular values over here, they are not going to be equals to 0. And since U and V are orthogonal matrices, orthogonal square matrices, sigma is a diagonal matrix, we have this A equals to U sigma V transpose. This is obtained by the SVD of A over here. And we can simply flip this guy. We can simply bring this V over here onto the left hand side of the equation by taking the transpose, because for an octagonal matrix, the inverse is equals to the transpose of the same matrix itself. So we'll get this relation AV equals to U multiplied by sigma over here. And since V here, it consists of V1, V2, all the way to Vn, and U here consists of U1, U2, all the way to Um, and we can rewrite this relation into AVI. This means that I'm taking one of the column here and then multiplying it by A over here, as well as UI sigma I. This means that I'm going to take one of the columns here and directly multiplying it with the scalar value of my sigmas over here. And this equation will hold true for I equals to 1 all the way to I equals to n. And what's interesting here is that since we have this relation of AVI equals to UI sigma I over here, and where this is a singular value, is a scalar value multiplied by our vector UI over here, and we'll see that AI or AVI over here, this guy over here on the left side, is the minima when the singular value here is also at its minima, or the product of these two terms here are at its minima. Hence, it corresponds to the singular or the smaller singular value at sigma n here. So because since when we compute the SVD in the previous slide here, it's always computed, or any or compiler that you are using, Python or MATLAB, for example, when you compute SVD, it's always going to arrange it in this way, the singular value, from the largest all the way to the smallest singular value. And hence, the column of V that corresponds to the smallest singular value is going to be at its minima over here, since it corresponds to the smallest singular value here. And hence, this will give us the solution to the optimization uh, cost function, or the least square cost function that we are after. So we are after this where AH should be the minima and subjected to the constraint that the norm of h should be equals to 1. Since and this what this means here is that h here would be at its minima when we choose v or vi that corresponds to the singular value that is at its smallest value. And we'll also be guaranteed that the norm of h would be equals to 1. This constraint here would be satisfied because v here comes from the column of a octagonal matrix of V, and where every column here, the norm of every column and every row would have to be equals to 1. Hence, the solution of the problem is or to this least squares problem over here is simply given by setting h equals to Vn that corresponds to the smallest singular value. So as I have mentioned earlier on, that the constraint of the norm of h to be equals to 1 is also automatically satisfied because V here is a octagonal matrix where every column and every row has to be unit norm. Here's a summary of the direct linear transformation algorithm for us to find the homography from 4-point correspondences or more than or equals to 4-point correspondences. So the objective here is given n equals to or more than 4-point correspondences, 2D to 2D point correspondences that is denoted by xi and xi prime. So what this means is that I have two images here, I1 and I prime over here, or I and I prime over here. I have the 4 or more point correspondences here. So this is x1, x1 prime, x2 and x2 prime, and so on and so forth over here. Given this observation from the image where I have this set of point correspondences, the objective is to find the 2D homography H such that xi prime is related to xi via this relation over here. And we have seen that the algorithm is very simple. For each point correspondences, we will compute AI. This is given by the equation of AI h equals to 0, which we derive using the cross product earlier. And we'll take the first two rows from this because we have seen that only the first two rows or only two rows in the cross product matrix are linearly independent. And then we'll assemble n of this 2 by 9 matrix of A into a 2m by 9 matrix of A over here. So we'll stack, this means that we'll stack all the A's, AI together, A1, A2, all the way to A n over here. And then we'll stack it together to form AH equals to 0. And finally, we'll obtain the SVD of A because the objective here is that we know A here or the point correspondences are corrupted with noise, and hence this equation here, the solution here is not going to be fully satisfied. And this is why we are going to just simply minimize the norm of AH over H subjected to the constraint that the norm of H should be equals to 1. And this we have seen that this can be easily done by taking the SVD of A such that we get the left octagonal matrix, the singular matrix, and the right octagonal matrix. And the solution here of H will correspond to the smallest, the vector or the vector in the right singular matrix that corresponds to the smallest singular value over here. In this case, I denote this as Vn over here. And then we'll be able to rearrange from H because H is a 9 by 1 vector that consists of all the elements in the homography matrix. And finally, we'll be able to rearrange this 9 by 1 vector over here to recover our 3 by 3 homography matrix here. And there is a degeneracy case where the formulation that we have seen earlier would fail. So in this case here, let's start off with the AH equals to 0. And here we know that a solution or a right null space of A for the solution of H exists for this null space equation here is that the rank of A must be equals to 8 for the solution of H to exist. This is because H over here is a 9 by 1 vector with 8 degrees of freedom. Hence, the null space, to fulfill this null space equation, the rank of 8 or the rank of A must be equals to 8. And in the case where the rank of A drops below 8, if uh, 3 or of the 4 minimal 4 points correspondences are collinear, this means that I have the correspondences and 3 of them actually lies in a straight line and 1 of them is outside the straight line. So what this means is that these 3 points, they become linearly dependent on each other because they all lie in a straight line. Given any 2 points, I'm able to compute the third one. So this means that they are not linearly independent, and hence the overall rank of A will drop below 8. This means that the total number of constraints, which is given by the rows, the linearly independent rows in A here, it will no longer be equals to 8. Since 3 of the points are linearly dependent on each other, and hence the rank of A will be lesser than 8, and this means that I will not be able to solve for the null space of A to get H over here. And in this case, we call this a critical configuration or a degeneracy case, where the solution of the H here would simply not exist. And hence, it's important to check that the selected points, the correspondence points here, are not in the critical configuration. The collinearity of the 3 points can be easily checked via this formulation over here. Given any 2 points, we can find the line. So x1 and x2 over here, we can simply compute the line as the cross product of these 2 points. And a third point, any third point, if to check for collinearity, suppose that this third point here is x3, we will simply put it into this equation, L transpose of x3. If it is equals to 0, this means that these 3 points are collinear. And if it is not equals to 0, then this means that the 3 points are not equals to 0. And we have seen earlier the direct linear transformation algorithm, which simply to formulate the formulation or the estimation of the homography into AH equals to 0, the homogeneous linear equation here, such that we can make use of the known correspondences to form A and solve for the unknown of H here, the 9 by 1 vector of H here. But there is a problem in the observation, which will result in a ill-conditioned matrix of A that will lead us to the wrong solution. Here's an illustration of the problem. Suppose that I have a point x, y, and w, homogeneous coordinate of the point on the image, which is given by 100, 101 over here. And suppose that x prime, y prime, and w prime is also in this order, hundreds on hundreds, and also 1 over here. The scale here is set to 1. And by putting it into AH equals to 0, formulating A here, the matrix of A here, according to what we have derived in the previous slide, this is what we are going to get. The 2 by 9 matrix of AI over here is what we are going to get. We can see that from here, some of the columns here, it's going to be in the order of hundreds, and some of the columns here are going to be in the order of ones, and some of the columns here, because of the multiplication of the two terms, is going to be the order of 10,000s over here, 10 to the power of 4 over here. And the order of magnitudes difference is going to cause a bad behavior in SVD. So in linear algebra, we call this kind of matrix ill-conditioned matrix, and this will lead to a very bad behavior in the SVD solution. I won't go on to prove this. I'll leave this to you because it's out of scope of what we are going to teach in this semester. And but I'll illustrate this with an example here. Suppose that I have 5 points that is selected from one image, and here these 5 points are corrupted with noise. Each one of these points is corrupted with noise in 100 times, 100 different noise over 100 different trials. And every time these 5 points are corrupted with once with a 0 0.1 pixel Gaussian noise, we'll use that configuration to compute the edge that transfer any one of these points to the next image over here. And over these 100 trials, because this is corrupted with 100 different randomly generated Gaussian noise of 0 0.1 pixel standard deviation, what this means is that it's going to the transfer of the point from my the homography that I have computed over 100 trials, uh, it's going to end up in 100 different locations here. And we can see that if we use a unnormalized data to compute, this means that all these points over here, they are unnormalized. They are lying in the, this means that the A matrix that I have formed from this unnormalized data over here, it's going to have a different order of magnitudes over the different columns that we have seen the example in the previous slide. And to use that to compute the transfer or to compute the homography for the transfer, we can see that the transformation here, the transfer of the points over these 100 trials, of each 1 point over 100 trials here, it's going to end up to have a very large error distribution compared to a normalized data, because in this case here, this A matrix is ill conditioned, and uh, compared to a better condition, a well-conditioned A matrix to compute the homography, we can see that over 100 trials, the transfer of the points over 100 trials is going to lead to a very small error over here. And therefore, we have to mitigate this particular problem. We have to turn A into from an ill-conditioned matrix into a well-conditioned matrix. And this can be done by normalization. We'll look at how to do the normalization to achieve this. So normal data normalization is carried out by simply a transformation of the points as follows. First, all the points are translated so that their centroid is at the origin, because we have seen that the scale of the points, given an image, the scale, the magnitude of these points, it actually matters, because if it is 100, 101 versus another point which is at, for example, 1, 1, and 1, then the scale of this or the distribution of these points are too large, too far away. Hence, as a result, it will lead to the difference order of magnitudes in our formulation of the A matrix. So we are going to first centralize, or we are going to first centralize all these points with respect to their centroid as the reference point, so that they are all centered to the this centroid. And then the next thing is that we are going to prevent some points from being too far away from each other by scaling, by applying an overall scale such that the average distance of all the points to the centroid here is equal to the square root of 2, and the transformation is applied to each of the two images independently. This means that the average point is equals to 111 after the normalization. That's why we have the square root of 2 here. And this will, as a result, mean that there won't be any magnitude difference in the linear equation of AH equals to 0. Uh, Here's a summary of the normalized direct linear transform algorithm. It should be noted that the data normalization is an essential step in the DLT algorithm, and it must be done in order for us to get the correct result. So this means that this step here is not optional, it's compulsory. Otherwise, we will not be able to get a correct result. So the objective here is, as usual, that given n equals to or more than 4-point correspondences, 2D point correspondences, we want to determine the 2D homography such that xi prime equals to hxi. We want to transfer a point from one image to another. So we'll start by first normalizing the points by computing this. So what this means is that we are going to apply a transformation on our every of our point in image I here, and we are also going to apply another transformation on every image point xi prime on the second image. Notice that t norm and t prime norm, they are not the same, because we will compute the transformation of each image individually, because the centroid and the scale are not going to be the same in the two image, because the distribution of the points are not going to be the same, since it has already undergone some homography transformation here. And here's the formulation for the matrix. This is a 3 by 1 transformation matrix over here, whereas here is our scale. It's computed by square root 2 divided by the mean distance of all points from the centroid. This means that if I have an image, I have all the points over here, and I compute the centroid. The first thing to do is to compute the centroid over here, which I denote as Cx and Cy over here. And then we'll take the average distance. We'll compute all the distances with respect to this new centroid, and then denote this by, take the average and denote it by bar of d, and compute the scale as square root of 2 divided by d bar over here. So by applying this transformation, we'll ensure that all the points now are centralized with respect to the centroid, and as well as their mean average distance is going to be 111 from the centroid. And after applying this, we'll get the new set of correspondence point xi tilde and xi prime tilde. Then we'll use this set of point correspondences to compute the homography. And finally, we'll have to denormalize the solution. This means that we'll apply this transformation to the h tilde, which we have computed from the normalized points, to denormalize it to get the final solution of h here. And please remember that this step is not optional, it's compulsory to do this. Otherwise, we'll end up with a ill condition matrix of A, and that will lead us to a bad solution of the homography.